Hello again, this is Tom from Every Step Calculus, everystepphysics.com. This is going to be a physics problem video concerning a modified Atwood machine and how to do it in my program. So you put physics in here with open and close parentheses to get to the menu, my main menu, after you purchase my programs. And we're already at Atwood Machine. You can scroll with this cursor here up or down or to find the proper menu item that you're looking for. Modified Atwood Machine has a table and a pulley and a mast that's hanging. A regular Atwood Machine has just a pulley and two masses on each side of it with a pulley and with a rope. So we're going to choose that one. I show you the picture. Here's M1 on the table and mass 2 hanging. And we're going to choose number 3 because that's what they give us is the mass on the table, the mass hanging, and the mass of the pulley. And they also give us the radius in this problem. They might give you this one here, number 2, mass hanging on the table, mass on the table, mass hanging, radius, and the moment of inertia. But whatever they give you will answer it with my programs. I choose number 3, and we're going to enter the mass on the table. You have to press alpha before you enter anything on this entry lines here. So it's alpha 3 for this problem on the table. Kilograms, I do the conversions for you in case they give you whatever. I'm going to enter the mass that's hanging. Alpha 4 kilograms. Mass of the pulley is given as alpha 1. Sorry, alpha 1 kilograms. They give us the radius as alpha 0.02 meters, number 3. I always show you what you've entered. You can change it if you want. This all looks good to me. Press OK. Moment of inertia is with this formula here. 1/2 the mass of the pulley times r squared. And I gave you also the free body diagram of it. Here's the mass on the table, the way you draw it on your paper. Here's the mass hanging, T2, M2, the tension. This is Fg down here, force of gravity, equals mass times gravity, really. And I gave you the free body diagram of the pulley, the torque of the pulley, tension of the pulley. Here we go here, tension T1 and T2. You draw it just like that. I can't draw a circle, but you can get the idea. And we're finding the linear acceleration of mass hanging. Here's the force of gravity. And the formulas are very important. You've got to write this down. T1 equals tension of the string. You don't have to write that down, but you can go T1 equals the mass 1 times acceleration, linear acceleration. So T equals ma. It's Newton's second law, really. And then the tension of mass 2, string of mass 2, which is connected to m mass 2, is equal to the mass 2 times gravity minus the mass 2 of the acceleration. Now, T is the torque. It's a turning force, and it equals the force times the radius. It also equals the moment of inertia times the angular acceleration. So write that on your paper. You don't have to write torque, maybe. You don't have to write a turning force. I'm just doing that to let you know what these abbreviations stand for, etc., which always bug me in physics because they never tell you that, so you don't know what they're talking about. And then I give you the definitions of what's in these formulas too. And the torque of T2 minus the torque of T1 is equal to the moment of inertia times angular acceleration right here. So we have our formulas which we're going to use, which is times R, force times R equals moment of inertia and angular acceleration. And that equals, we substitute torque for this formula here for these, work out this algebraic equation, okay? Now we're going to convert this angular acceleration to linear acceleration by dividing by R. A equals R in the formula, okay? When we do that, the R's will cancel. All the R's cancel, okay? And so we get this equation here, T2 minus T1 equals 1/2 M3, which is mass of the pulley, times linear acceleration. We substitute what we found for the formulas for T1 and T2 here. We move A's to the one side for algebra. We're trying to isolate this linear acceleration, right? We got minus signs here. We get rid of those by multiplying times a -1 on both sides. And then we factor out linear acceleration here. We factor it. It equals force of gravity of M2. And then we divide by what we factored here for the linear acceleration and move it to the other side here, and here's the formula. Here's the equation for our purposes, okay? So we're going to put all the variables in, which we do here, and we solve for it. And with the calculations, it equals to 5.232 meters per second squared. I also do the angular acceleration for you, which is divided by R. Linear divided by R equals 261.6 rads per second squared. This is divided by 0.02. I do the tension of string 1, 15.696, which we found the formula for mass times acceleration for the formula here for T1. And we now know the acceleration, so we can put that in there. And T2 turns out to be 18.312. Remember to always write sloppy on your tests, because that's what all nerds in physics do. The geniuses that go through these classes and the professors, they all write sloppy. And so make sure you kind of scribble this stuff down, and then you'll get an A in the whole problem, okay? All right. Go to my site, buy my programs, and have a pass calculus. I mean, not calculus, but physics. Well, you do that too if you buy my calculus programs, but go to my site, buy my physics programs, and pass physics, okay? Have a good one.